Hey everyone, let's look at a trickier translational problem right here. We have two masses that are connected together with a spring and a damper. In the first portion of the class, you'll probably only worry about one-dimensional systems. So when you have a system like this that's in two dimensions, try to convert it into a one-dimensional system, right? What are the forces that are acting upon this system? Well, you have a force that's going this way, and you have a force that's effectively going in the same direction for the second mass. We're going to label these masses M2 and M1. And you're told that your angle right here is alpha. And you make that an alpha, not a gamma or whatever the heck that was. So that's an alpha. Well, we can actually draw the normal forces and the gravitational forces and then find the resultant vector by just doing this. Right, that's the gravitational force, that's the normal force. Let me pull that normal force down, and then the resultant vector is equivalent to the force that's acting on this mass in that dimension. It's the same thing for M2, and we know that this is going to be alpha, right? So what are we going to do with the alpha? Well, we're going to find this resultant vector right here because we know this is m1g, which is the force. The resultant is m1g sine alpha because sine is equal to opposite over hypotenuse. We know that the hypotenuse is m1g, and then when we multiply it over to the other side, we get m1g sine alpha is equal to the opposite. The same thing for m2, so we have f1 is equal to m1g sine alpha, and f2 is equal to m2g sine alpha, right? So since we have our two forces, we can erase everything else that we have here. So we already know what the forces are in that particular dimension, the one dimension that we are talking about. And we'll go with our bond graph. We need to figure out our ones and our zeros. How do we know our common efforts and our common flows? Right? So common effort. Common effort is going to be, you know that here, let me highlight, that the forces between this damper and this spring could be different, but the displacement of those two are going to be the same, because say that we're going to take this as the displacement of mass 1 and this is the displacement of mass 2. As mass 1 and mass 2 move, the displacement of the spring and the damper is going to be the resultant between those two. It's going to be the difference between m2 minus m1, which is going to be the displacement of that spring and that damper. But the forces aren't going to be the same because the spring constant and the dampening constant could be different. I mean, they could be the same, but they're most likely not going to be the same. It would be pretty cool if they were the same. But what we're going to do is now we're going to say, awesome, great. We want a one junction right here. We also want a one junction for the masses because they move by themselves, but they move independently, and they actually move at the same velocity with their forces that are acting on them. Right. Next, we have zero junctions in between these certain fields. Right. So let's say that, for example, let's say that we're going to take our start point to be here. You can make your start point here if you want in terms of propagating that force, but I'm going to arbitrarily choose that it's going to flow in yay direction right here, this direction right here. So how are we going to figure that out? Well, I'm just going to put a 1 right here to start our bond graph. Okay, I'm going to put a 1 right here to start our bond graph, and going into this 1, because we have that mass right there, we're going to do F2 is going to go into the bond graph. What's going to come out of the bond graph is going to be that M2, that inertial component, right? That's going to come out. It's effectively a mass, stores energy. Next, we're going to go into a common force junction right here because, as I said, the force will propagate to the damper and the spring as one system and the mass, right? Because inline components, say that we had an inline component like this, the forces will be the same through inline components, and these two are effectively inline components when you think about them as such, right? And so we're going to do that, and we're going to put a zero junction right there because these are two inline components that are connected together, and we also have two ones that are coming out of their common flow junctions. Right, we have this one right here and this one right here. And connected to those one junctions, we have a spring on one side, which is a capacitor, and we have a resistor on the other side, which is a damper, right? And these constants are going to be 1 over K for the capacitor, and for the resistor, it's going to be B, right? So we have those, and then for the one junction right here for the mass, we're doing something quite interesting, right? And we're going to say it's coming out of the system is going to be the mass right here, M1. There's something going into the system as well. It's going to be F1, right? So F1 is going into the system, right? We could stop it here, or we could say that we're given this plane. Do we know if there's friction or not on this plane? Well, there might be. So we could just effectively say there's a friction that's coming out of this, right? Well, you could say, yeah, you said that, but there could also be friction right here. Yeah, there could. So you could actually add that as a component into this first mass right here is going to be this friction component right here. You can add that resistance to that friction component if you want, and that would be totally valid, right? But maybe there is no friction between the masses. But it's a valid assumption to make if you want to go through and make that assumption, and your equations will still be correct, and your state space equation will work out, and everything will be good in the end. But I'm just going to choose not to do that, just to match this problem that I'm working on for now. So I'm going to assign causality. First, we'll assign causality to the forces, right? And so the sources of effort, causality goes yeah. Next, I'm going to assign causality to the masses, okay, because it's usually on the other side. Next, we're going to fill in the gaps, mostly. So right here, we're going to fill in the gap right there, and then we're probably going to do, okay, let's make this the causality, right? Might as well, right? And then we have to make this here too, because the only component right here with the flow has to be that mass. Okay, so that does actually go right there. We're done with the zero junction. Next, we have to make these the causal elements right there. So as you can see, what I did was I put the causalities for the masses, I put the causalities for the forces, and then everything else went into place and made it easy for us to figure out the causality. But this is the bond graph that you get. In the next video, we're going to come up with the state space equation for this bond graph.